Okay, last time we just began talking about the 5 different patterns that you can use for drawing resonance structures. The first to notice is an allylic lone pair. So we talked about this one. So the allylic position is any position that's right next to one of the carbons in a carbon-carbon double bond. So the nitrogen atom at the bottom here does have an allylic lone pair. So we can draw a resonance structure of that. But the nitrogen at the top, that lone pair is not allylic. It's not directly next to a carbon in an alkene. And so you can't draw a resonance structure that has anything to do with that top nitrogen atom. You can try, but you'll break one of those 2 rules for drawing resonance structures. You can't make or break single bonds, and you can't give an atom more than an octet. Okay, so that was our first one. The second pattern is, instead of an allylic lone pair, an allylic carbocation. And so this actually doesn't work as similarly as it sounds like it should. So So there's an example of an allylic carbocation, right? So the carbon that's got the positive charge is right next to the carbon, or to a carbon that's in a CC double bond. So that is an allylic position. When we did the lone pairs, though, we started, of course, from the lone pair and went sort of toward the alkene. But here that isn't going to work, because our curved arrows show the movement of electrons. And so this positively charged carbon doesn't have a lone pair to work with. And so we're actually going to go the other direction, and we're going to start from the pi bond. And so those electrons are going to move toward the positive charge. And so we're just going to scoot the pi bond over by 1 position. So that pi bond is going to stay the same. And then rather than going between carbons 2 and 3, that pi bond is going to go between carbons 1 and 2. Now we have to deal with the positive charge. It used to be on carbon number 1 on the end, but that carbon has now gained some electrons from that pi bond. However, the carbon in the very middle of the molecule, carbon 3, I guess, has lost electrons. So it's going to have a positive charge. Now, we still have an allylic carbocation, but in this case, it's allylic in 2 different ways, right? Because it's got those 2 pi bonds. And so we can mess with the other pi bond as well. So we can do that. And so we can have that 3rd resonance structure. So if we have multiple pi bonds, that can participate in the same, not necessarily the same resonance structure, because you could have pi bonds in two very different parts of the molecule. But if you have a system like this where two of the pi bonds can all sort of, these electrons can move up and down all the way across the system, and maybe this is easier to see with that positive charge, which is not a requirement for this particular property, but it's easiest to see here. If you have multiple pi bonds that can participate in resonance together, we call that resonance. Sorry. Of course we call that resonance. Geez. Conjugation. We'll learn more about conjugation when we do aromatic compounds, which are a special kind of conjugated. But if we have a system with multiple pi bonds, multiple lone pairs, we say that all of those electrons are conjugated. Okay, 3 and 4 kind of go together. I mean, kind of. So we can have a lone pair next to a carbocation. Now, this one, when you see it, it's going to look maybe kind of obvious. Mainly because we're used to seeing something like that structure as like the second structure that we draw. So here we've got an oxygen with a negative charge and 3 lone pairs, and then we've got that carbocation at the bottom. So this is sort of screaming for that carbocation to get some more electrons, which it can easily because it's got a negatively charged atom right next to it. So we can move a lone pair of electrons to make a double bond. Two lone pairs now on the oxygen, and we've satisfied or canceled out the charges. So I say this is a little backwards because what you would probably start with is that molecule, and it'd be like, okay, draw a resonance structure of this molecule. And so generally speaking, and we're going to talk about some additional rules for determining which of these two structures is more important in a second. But generally speaking, when you see a pattern like this, a lone pair adjacent to a carbon atom, a carbocation, that is not going to be the most important or the most stable resonance structure. Okay, number 4 is almost really 3 is a special case of number 4, I guess. Whatever. A pi bond between atoms of different electronegativities. Yes. And so, because essentially no two elements have the same electronegativity, you could just say that this is a pi bond between two different elements. So, well, 3 is an example, right? That pi bond is between a carbon and an oxygen. The oxygen is more electronegative than the carbon, And so when we draw a resonance structure, so I'll draw the arrow going the other direction as well. So we go to that structure. So do a very slightly different example. There's nitrogen. Like oxygen, nitrogen is more electronegative than carbon. And so well, there's two directions that we could move this pi bond, right? We could go up toward the nitrogen, kind of like we did with this one. Or we could go down and put the lone pair on the carbon. And so that would look like that. Now, both of these are valid resonance structures, but one of them is much, much better than the other one. Again, we're going to talk about these rules explicitly in a minute. Which one do you think is better, one or two? One. So nitrogen is more electronegative than carbon, and so it's more willing to have more electrons. And so if we draw an arrow toward that more electronegative element, that's good because we're moving electrons toward it. And so in the on the right, the structure at the top, that nitrogen has a negative charge, and nitrogen is happier with a negative charge than carbon. And in the structure on the bottom, the carbon has a negative charge. Also note that there's an octet issue here with this carbon. There's only 6 electrons. Again, not an issue, but it'd be nice to have a full octet. That carbon only has 6 electrons, and actually same goes for the nitrogen at the bottom. But the main thing is that the more electronegative atom would like to have those electrons. Okay, we talked about benzene last time, I think, and benzene is essentially the last example, although it's not just benzene. Benzene and some other compounds that are like benzene. But we can have conjugated, and in this case, it's just going to mean alternating pi bonds in a ring. Should make this bigger. Sorry. And what we can do here is essentially scoot all of the bonds by one position at the same time. And this is a unique property of rings like this. And this is one of the reasons why these molecules are really stable and really common. So in this case, we're moving each pi bond clockwise by one position. And so that just ends up right? In this case, just rotating the molecule.
Does it change any properties of it or no?
What about properties?
Does it change anything like the ring or just the same properties with or
Good question. So I previously I talked about the resonance hybrid being an average of the two different or two or more different structures that we draw. And in this case, the benzene actually has kind of a special resonance hybrid. So if we draw our dotted lines, we would do it kind of like this. But in practice, and you may have seen this before, we often kind of cheat and just draw a hexagon with a circle in the middle. And that also means benzene. Now, when you end up trying to draw individual chemical mechanisms where you're breaking pi bonds and stuff, this abbreviated structure doesn't work, but it's a resonance hybrid. It's not really meant for that sort of thing. But if you see in the chemical literature or anywhere else, that sort of thing, that's a benzene ring as well. Okay, so those are our 5 patterns. That really covers all of the different resonance structures that you're likely to see. But of course, they can be combined with each other or have like multiple of the same pattern over and over again. So you should be ready to recognize those when they come up. Because at least the arrows that you draw are really always going to be the same as I've shown in these couple of examples. So the last thing we need to do is talk about how to determine which resonance structure or resonance structures of one particular molecule is better. Better is an okay term, I guess, because we still have those 2 rules: the not making or breaking single bonds and not exceeding an octet. Those are like the hard and fast rules. But these kind of rules are going to help you determine which resonance structures are really good and accurate depictions of where the electrons sit in the molecule versus other ones that don't give a very good picture but are still technically okay based on the 2 big rules of resonance structures. So the main thing here is that all the resonance structures that you can draw don't necessarily contribute equally to the resonance hybrid. For example, in benzene, the 2 resonance structures do contribute equally to the hybrid, but it's not a super common case. And the reason that we care about the relative importance is a lot of what we're doing in organic chemistry is predicting reactivity. And if we can figure out which resonance structures are better than others, we can see where the electrons are in the molecule. And then that's going to tell us, which position is going to react with which other position and so on. 4 rules. So the better resonance structure, or the resonance structure that contributes the most to the hybrid, is going to have, first of all, greatest number of filled octets. So what do the octets look like here? Okay, well, we've got the carbon over here, the C plus, the carbocation, has 6 electrons, right? No lone pairs and 3 bonds. So it does not have an octet. Then the question is, can we draw another resonance structure of this molecule where all of the atoms have an octet, or where we can satisfy that carbon's octet? The answer is yes. We can move that lone pair down to make a pi bond. Okay, so we start there initially, and then our lone pair has moved down there. Okay, the carbon no longer has a formal charge, but the oxygen does. The oxygen is going to have a positive charge. Okay, and then for our octet, okay, great. The carbon here now has an octet, 8 electrons, and you might also be curious about the oxygen, so you can check that as well. Okay, on the left, 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're good. And on the right, 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay, so the oxygen, at least when it comes to the octet, is not an issue here, just the carbon. Okay, so which of these structures contributes more? Well, it's going to be the one that has the greatest number of filled octets. So we'll say that this is the major contributor. And the one on the left is the minor contributor. The one on the left is not wrong, but the resonance hybrid looks more like the structure on the right than the structure on the left. Okay, the next rule is you want to have all things the same with rule number 1. You want to have fewer formal charges overall. Okay, so this molecule doesn't have any formal charges, so I'd say that's pretty good with this rule, but we can draw some other resonance structures of this. For example, like that. Or we could draw this. Split the pi bond between two atoms at different electronegativities. Okay. This is going to require both rules, in fact. So I think we can see the major contributor is going to be the first structure because it doesn't have any formal charges. And that's good. The other two both have a positive and a negative formal charge. The difference is that the structure on the right has that carbon with 6 electrons. So that's not a full octet. And that's actually rule number 1. We want to have the structure with the most filled octets. And so deciding between structures 2 and 3, or middle and right, the one on the right is going to be the smallest or most minor contributor because it breaks both of the rules. And then
Presentation. Yeah.
that one kind of fits somewhere in the middle. As we mentioned before, having negative charges on an electronegative atom is a good thing, better than having them on an atom that's not as electronegative. So if we have this molecule with a negative charge on the carbon, here this lone pair on the CH2 is adjacent to the CO double bond. And so we can draw a resonance structure that involves those. So we can form a pi bond between those two carbons. And then I should draw the lone pairs that are already on the oxygen. So we can do that. Two lone pairs are already there. Okay, so the lone pair on the CH2 comes down, becomes a double bond. The CO double bond is going to move up to become a lone pair on the oxygen. And now that means oxygen has a negative charge. Charges are good there because you have to conserve charges between different resonance structures as the same molecule. And okay, so the difference here, there's no difference in octets. All of the atoms in both versions have an octet. That's the first rule. Second rule is the number of formal charges. Okay, well, we just have one negative charge in both cases. And now we want the negative charge to be on the more electronegative atom, which in this case is oxygen. And so that means this will be our major structure, and that will be the minor structure, contributor. Those three rules will take care of most examples. But if you don't have, and this generally will happen if you don't have any heteroatoms in your molecule, and you're just dealing with resonance structures between different carbocations, you want that carbocation in the major contributor to be more substituted. So this looks a lot like our previous example. This is one of our patterns. Actually, all of these have been a pattern, but this is an allylic carbocation. And we know we can draw a resonance structure of an allylic carbocation by moving the pi electrons toward that positive charge. So pi electrons move over here. And the positive charge, well, the positive charge doesn't really move because this positive charge is a lack of electrons, but the carbon in the middle is now electron deficient. So it's got a positive charge. All right, so the more substituted carbocation is the major contributor. And I think we can see here that the structure on the right has more substituents, on the carbocation than the structure on the left. So we can summarize this with a little table. Okay, there we go. So if we have no non-hydrogen groups on the carbon, so all of the substituents, quote unquote, are hydrogens, that's just CH3 plus. Right, carbocations only have three things attached to them. It could be hydrogens or other things. So this is, right, CH3 is a methyl group, so this is a methyl carbocation. And these are the least stable. If we have one non-hydrogen group, that would be like this. So that is similar to our minor contributor in the example. This is a primary carbocation. It's going to increase in stability as we go along. We have two groups attached. That's secondary. Three is tertiary. We can't have a quaternary carbocation because it can only have three things. And tertiary carbocations are the most stable. So if you could draw a resonance structure that creates a tertiary carbocation, all other things notwithstanding, that will be the most stable, highest contributor resonance structure. We're going to talk a lot more about carbocations in chapter 7, mostly. And so we'll come back to this and sort of be grilled into your brain, I think, even more in that case. But for these purposes, we'll just leave it at this. Okay. So I'm going to give you a molecule that has all the resonance structures. Fine, I'll draw you some lone pairs. There we go. So see how many, actually, I don't know what the answer is. It's probably like 8 or 9 or 10. It's a bunch. But see if you can come up with some alternate resonance structures for this molecule. And as you come up with, a handful, look back at these priority rules and see if you can determine which ones are greater contributors than others. So if you need a starting point, go back to the different patterns and see if you can spot any of those patterns somewhere in this molecule. By the way, this is cytosine. It's one of the base pairs in DNA. Maddie, do you want to give your spiel? I mean, well, they haven't started to think too much yet, so okay. Mhm. Oh, well. Uh, Okay, there's some that I came up with. The first thing I did was bring a lone pair on this NH2 down to form a pi bond and then break a pi bond to make a lone pair. As you can probably see, that's a really common motif that happens in resonance structures, is a lone pair becoming a pi bond and a pi bond becoming a lone pair. Then I did the same thing again. I took a lone pair, made it a pi bond, and then took a pi bond and made it into a lone pair. Then I kind of reset the molecule because I needed to draw some different arrows. So now I took a lone pair on the a different nitrogen, made a pi bond, broke a pi bond, made a lone pair. And then maybe the most interesting one is this bottom center. So this is the same pattern as the benzene ring. And maybe it would make more sense if I redrew this like that to make all the pi bonds in the middle of the ring. But this is that 3 arrows all going clockwise or counterclockwise thing. And it's okay that we have nitrogen atoms in the ring. We could have really any sort of atom. But we've got these alternating double and single bonds in a ring. And so we can draw a resonance structure like that. And you can see these two structures here are the same, except the pi bonds in the ring have just been rotated around. If you came up with other things, that's totally okay, as long as you haven't broken the rules. Can't make or break any single bonds and can't exceed an octet. And your structures should be good. Now, assigning importance of these. So there's no, I'm pretty sure, at least none of the ones that I've drawn, there's no atom that does not have a filled octet, which is the first rule. So we can't use that first rule to differentiate between any of them. The second rule is the number of formal charges. So we want less formal charges. Okay, so these two structures are identical. So this, the starting structure is going to be the major contributor. That's not uncommon. We often try to draw things as their major contributor if they have resonance structures. Because all of the other molecules have formal charges. They all have one positive charge and one negative charge. Now, I could draw. Why don't I do that? I'll draw it based off of this one. Let's draw this. So I could draw this resonance structure where see if I can actually get everything else correct. Positive charge there. So we now have a lone pair and a negative charge here. We now have a positive charge on that carbon. So this is kind of a disastrous structure, not because we've broken any hard and fast rules, but because we've now created two sets of positive and negative charges. And so I guess if we base it off of all of these, this one is going to be, actually, I should probably call them one for the most major, two, 1, 2, 3, 4, 5, 6, the least contributor. Okay, so that takes care of rule number 2. But now all these 4 here that haven't been assigned yet, we'll have to go on to the next rule. So the next one is negative charge on a more electronegative atom. All right. So fortunately, in all of these cases, except one, the negative charge is on the oxygen, right? And then we have one case where it's on the nitrogen. Between nitrogen and oxygen, which is more electronegative? Yep, oxygen. So that means that the three structures where the negative charges on oxygen are better than the one where the negative charge is on nitrogen. Okay, so that makes this one the second least contributing structure. And then the next one is the last rule is more substituted carbocation. And that's not an issue here because our three remaining structures don't have any carbocations. So based on these rules, we could say that these are, well, they're all they're all equal and they're kind of in the middle. Now, there's technically a few more rules that you could get into really nitty-gritty about all of the details. But for our purposes, we'll say that those three are equal contributors. Questions on how I got to that? Does anybody have another resonance structure that they want for me to check and or show off to everybody else to check? That's okay. Okay, so this is basically the homework. All right. So let me look at PS5, PS5. Should probably put up the answers to the other ones for this, but yeah, so it's one giant problem with tons of examples. And the only ones I want you to turn in are A, B, and C. And then do the rest for practice. So for each molecule, draw all possible resonance structures. There's a reasonable number of them for A, B, and C, and then kind of like this crazy example that we just did. I think there's at least one. Yeah, there's a complicated one where you're probably not going to be able to get all of them, and that's totally okay, but it's just for the practice. So like we did in here, you see how I haven't drawn the arrows between every resonance structure and every other resonance structure. That would be kind of ridiculous. I just kind of did it going from the first one to the second one to the third one. Then I kind of had to reset. And this is totally okay. This is kind of what I'm looking for. And just generally speaking, we're going to draw arrows going from the structure on the left to the next structure on the right. But that's not a hard and fast rule. And the curved arrows that lead from each resonance structure to the next indicate which structures are the major contributors to the resonance hybrid. So mainly I'm just looking for the number one major contributor, although you should be able to rank all of them like we just did. Although I wouldn't do that to you on an exam. Questions on this? Cool. All right. That's all the new material for chapter 5. So this homework isn't going to be due until 2 lectures. I'm not going to pull the homework up just because we're already done with the content. But next time we'll start with chapter 6, which is acids and bases. In that chapter, rather than using arrows to kind of show this whole resonance business, we're going to actually do some chemical reactions with the resonance arrows. All right, office hours are going to be in here for the first at least little while. So if you want to talk to me, you can just stay here. All right, thank you.